Okay. That's where we were yesterday. We needed to find the, we found the area of this, under the spiral. Right, so what's happened next? Let's just see. Well, that's our example. That's another example where substitution helps significantly. It's a result, it's something you know by fact, you know without computations. You know from the first year what the normal distribution is, what the density of the normal distribution is, that's the function, which is the density of a normal distribution. And you were told that this is truly density. One of the things which is implied by that is that the integral of this p of x function is 1. It's said right here. You know, we're shown the argument for that. The argument now, after we know substitutions, after we know double integration, the argument is simple, just fits on one slide. Look at this, what they say. You just give a name to this integral, or half of this integral, because this is a complete integral from negative infinity to positive infinity, whereas here from 0. So you give a name to half of this integral, and then you make this smart trick, you just take the I square. Why you do that? Because, well, it's because it leads to the result. That's the easiest explanation. You put them one next to the other, and in the second one you just rename your x into y, and then you use Fubini, because you have here product of two individual integrals, which by Fubini, if you use it the other way around, if you use in the reverse direction, you can make it like a double integral. The function is purely factorizable in the x and the y part. You have your rectangle, even though it's an infinite rectangle, but still it's a rectangle, and that's what you come up with. And in this double integral, because you're looking at the expression x squared plus y squared, it's a good case for polar substitution, the one which we done twice yesterday. If you do polar here, so that's my x squared y squared, which suggests polar. If I do polar, that's what it's going to be. X squared plus y squared becomes just r squared, but then you have extra r factor, which is the Jacobian factor which you need to introduce when you do polar substitution. And the things just change, this extra r factor changes the whole thing entirely. For the exponential negative x squared, you can't find antiderivative, you can't. But when polar brings another r, then by doing a simple one-dimensional substitution trick from the first year, you can finish the evaluation. You make a substitution. Well, first, in fact, actually, here again, you can use the fact that the function is purely factorizable in the pure theta and pure r part. So your double integral across this rectangle with one side pi 2 and the other side infinity, from 0 to infinity, you can factorize into the product of two individual integrals. That's what's done here. In pure theta integral and pure r integral, two one-dimensional integrations. First one is simply pi on 2. It's the integral of a constant. The second one, for the second one, because of the r factor, you can easily predict antiderivative. Here it is. Negative r half e negative r squared. That's the antiderivative. With a double substitution, even there. Infinity here, when you sub it into your exponential, because exponential decays to 0, that's why the value is 0 here. With a double substitution, you come up with the value 0.4. And that's the value for I squared. And we were interested in I alone. So by taking root of this, and by doubling that root, because half of the integral, right, from 0 to infinity, here's a negative infinity, positive infinity. By taking a root, doubling that will deliver the value of this integration, and that will convince you that this function has integral 1. Yes?
Just with the half theta squared, is that supposed to be theta instead?
Yeah, it's supposed to be theta. That's a typo. Yes, thank you. So it's a very, well, the typo really hidden. Thank you for spotting that. That's right. That's a theta. Normally, if I were doing something like this, I would never write something like this, actually, because, well, I mean, like if you've been listening to my integrals a lot, you know that normally when I integrate a constant, and that's a constant, I just say integral of a constant is just equal to the length of the underlying interval times the amount of a constant. So the length here is pi on 2, constant is 1, the interval must be pi on 2. I always skip this stage. I never write the antiderivative for the constant function. But on the other hand, that's a typo. Yeah, I'll fix. If I remember, I'll fix this. And that's the value for the integral. Okay. These are the other two substitutes. Yes.
But it shows 1.
Well, because here the integral of the exponential, and here's the exponential, which is normalized by 1 on root 2 pi.
Oh, okay, yeah.
Yeah, when you multiply by the extra 2 here, it will be 2 root 2 pi. 2 root pi's, and that's the canceling of the 2 root. Yeah, I should say root 2 pi. Let's just double check everything. The integral I square ended up to be pi on 4. I'm fine with this. I itself will be root pi on 2. We double this to make up the complete real line, which will be root pi. I'm sorry, yes, because it's the other thing here involved is here you have negative x squared by 2, which you don't have here. So there is a bit of an extra computation, so substitution, which lead to the 1 here. They are missing on the slide, and I guess the slide expects you to be able to do it on your own. Yeah. Any other questions? Okay, so the other two substitutions which you need to know, one of them is cylindrical one, the other one is a spherical one. When I say you need them to know, you need to know the geometry of these substitutions, what sort of areas they take to the other type of areas. I mean, the typical cases, which happens with the spherical or cylindrical substitutions. The other thing which you need to know is the Jacobian value for both of them. You can double check this. You can take the formula for the Jacobian with all the partial derivatives, and you can compute that determinant. I'm not going to do it today in class. For us, what's important, or for you, what's important, especially when you're going to use this, is the value for the Jacobians. They're very easy to remember, especially for cylindrical one. The value is the same as for polar one, it's just r. For the spherical, it's a little bit harder to remember, but still, I think it's doable. So that's the value of the Jacobian for the spherical substitution. There's one example in this set where we need the spherical, substitution. It's the one on the next slide. I'll discuss this with you. Yeah, we have plenty of time. It's this example. If you took the slide, the handouts of the website in the beginning of the week, I made some alterations to the slide. I just inserted here the GNU plot commands, which will help you to see the region, the volume of which we need to compute. So look at this, what it says. Using cylindrical or spherical. Spherical, I think it's a better way to use it. It's an easier solution when you use spherical. Maybe cylindrical will be almost the same. By using one of these substitutions, or one of these coordinates, cylindrical or spherical, find the volume of the region bounded by the cone. It's a cone at the bottom and a sphere at the top. If you want to see these regions, I inserted here the GNU commands, which will help you to see that region. In fact, I had it open before I come here. Hopefully it didn't disappear. Yeah, here it is. Well, actually, it's not. It is because I just cut a wedge out of it to make it even more stand out. What's happening here? So at the top you have this part of a sphere. Let me just bring the wedge back in. So let me just see command for the GNU plot. If I want to bring the wedge back in, that's the one with the wedge. So here at the top, it's a purple side. It is the dome of a sphere. At the bottom, it's a cone. And that's what GNU will plot for you if you use those commands on the slide I inserted. Our job here is to find the volume of this ice cream cone. Sometimes people call it ice cream cone, even though it's very little of ice cream in this cone. Yeah. But still, why not? Ice cream cone. You need to find the volume of this ice cream cone. I have a detailed computation. I'll show you these computations. They are on my dynamic slides. So look back at the question first. The question says, we need to find the volume of the area bound by the cone at the bottom, sphere at the top, is my computations. This is my cone, which I convert to more canonical form. It's a canonical form of the cone, but in this canonical form I have to couple it with the extra assumption that z is positive, because otherwise it will take both the upper side and the lower side of my cone. That's a sphere. This is a canonical shape of a sphere. In fact, to do this question, you don't need to see the actual picture of the region. Everything can be done in terms of the inequalities, and I'll show you this. Look at this. So here's my spherical substitution from the slide before. Of this substitution, we know that rho, the radius, is never negative. We know that the theta angle, the, how do you call it, the longitude angle, right? The longitude angle normally is taken within these natural boundaries, negative pi. The latitude angle, well, it's a co-latitude angle, because the 0 corresponds to the north pole, whereas in the canonical latitude, the 0 negative pi on 2 corresponds to the north pole. That's arranged for the co-latitude angle, and that's the value for the Jacobian. These are the things we need to know to finish the question. So all I need to do now, I need to reinterpret these conditions of my region. I need to reinterpret these conditions in terms of my new variables, rho, phi, and theta. And that's the reinterpretation. Number 2, for the sphere, because we actually taking the region within the sphere, so actually within the ball, the condition, it just comes down to this. The radius doesn't exceed 2. The left-hand side, it comes from the natural assumption on the radius. You can even check this analytically. You can take the squares, sum of the squares of all of these right-hand sides with the basic trigonometric identity. You will see that this is just rho squared. Now, 1, the first condition, the cone condition, there are 2 here, z non-negative and this relation. Z non-negative, because rho is always non-negative, it just becomes the condition on cosine of phi. And within this region, cosine of phi non-negative in the first quadrant, when phi in this narrower region between 0 and pi on 2. That's my interpretation of this condition in the new variables. Within this full spread of phi of the co-latitude angle, only the first quadrant is the one which delivers positive value, because of cos here. Now the second condition in the 1, the cone condition, it's again, we just sub in right-hand sides in that condition. And that condition actually comes with this inequality, large, big, greater or equal, because we're taking the area above the cone. So z must be larger than right-hand side. So if I substitute that one, so here's this condition, you see I put the inequality here to reflect the fact that we take the area above the cone. This condition becomes, it's just direct substitution, or almost direct substitution. When you take the sum of the squares of the right-hand sides of these two right-hand sides, because of the basic trigonometric identity, sine squared plus cos squared delivers 1, you end up with this, which you start solving. You can cancel out rho square, positive number, that doesn't affect the inequality. That's the cancellation. Well, you can cancel out and divide by sine square, which will deliver cotangent larger than 3, or I prefer to do it in terms of tangent. Tangent doesn't exceed 1 on 3. And that solves to this. Again, we disregard the negative values for the cotangent because we already know this narrower region for the phi angle. That's why we can be sure that the tangent is positive. That's why only this piece of the inequality matters. And this inequality actually narrows down this area even smaller, makes it even smaller, because tangent within this interval between 0 and pi and 2, tangent doesn't exceed 1 root 3 here. And that's the finish of the reinterpretation. This original description of the region, in terms of the spherical coordinates, rho, theta, and phi, ends up to be these 3 independent inequalities. 1, 2, and we said nothing about theta, so we take this original unrestricted range for theta. 3 independent inequalities, double-sided inequalities, which means that the image of my ice cream cone, or pre-image of my ice cream cone, in the raw theta phi coordinates is the upright parallelepiped. Something for which Fubini works very easy. It's the upright parallelepiped with these boundaries in the raw axis, as these are the boundaries, and the phi axis, these are the boundaries. Sorry, these are the boundaries in the phi axis. In the theta boundary, in the theta axis, these are the boundaries. So if I now move myself into this new space, into the raw theta phi space, my integral, my volume originally, of course, it's a triple integral of the unity across my omega area in the xyz plane. After substitution, here's my repetition via Fubini. Very easy repetition. It's because my area, my region in the raw phi and theta space, it's the upright parallelepiped. And I can say even more, because here again, if you look at the function, it's purely factorizable in the factors, in the pure rho factor, in the pure phi factor, in the pure theta factor. And you have upright parallelepiped. Such triple integral, or such repetition by Fubini, ends up to be a product of 3 individual one-dimensional integrations. Here they are. 1 pure rho integral, 1 pure theta integral, and 1 pure phi integral. Fubini for the upright rectangles or upright parallelepipeds, when function factorizes, I know you like it when I say parallelepiped. I can say it even more when you have the upright parallelepiped. And the function is purely factorizable into the pure rho, theta, and phi factors. That's the best way to do Fubini. Each of these individually we can evaluate. First one, well, that's the evaluation. First one is rho cubed by 3 with a double substitution like this. Second one is my typical statement I say. When you integrate a constant, you take the length of the underlying interval and multiply it by a constant. Length of the underlying interval 2 pi, constant is 1, that's why it's 2 pi. And for the sign, antiderivative negative cos, everything else, I hope I did the arithmetic correctly. That's the value for the volume of my ice cream cone. So the question is, the solution itself, when you analyze this region, it doesn't really expect you to know to picture the image of it. Of course, it helps, but you can do analysis in the pure inequality way. Inequalities, inequalities, inequalities. Any questions?
This type of triple integral dx dy should be
Ah, thank you. This one I can fix quickly. Hopefully. Any other questions? All right, and on the other hand, I said you can do it with inequalities only. I don't encourage you to do that. Every time I encourage you to make a picture, either with your pen and the paper or with the GNU plot or with any other plotting software. It's always nice to make a picture. It just gives you more insight into the things, especially with the integration. So in fact, I encourage you to make pictures with some plotting software. That will build up your skills with the plotting software as well. Okay, so we're done with this. Let's just see what happens next. No, not this one. Well, the last few slides in this set, and they discuss some other applications of integration, and they're all about this center of mass thing. So the way we find the point where you can balance, when you can balance either one-dimensional object or two-dimensional objects or even three-dimensional objects. And the whole idea just explained first in the finite case. So that's what we know from the elementary mechanics. Elementary mechanics tells me that if I want to balance out these weights, position like so, I need to put the pivot point, if I want to find the position for the pivot where my weights will be balanced out without leaning left or right, this pivot point, that's the formula for the pivot point. So basically the momentums, so the length of the lever from x1 to the unknown pivot point times the mass sitting at the end of that lever. All of these momentums, if you add them up, they must be zeros. That's one of the momentum laws from the elementary mechanics, I hope you know. And that's if you solve it for the x bar, that will deliver the coordinate for the pivot point in order to balance this, in order to keep this balanced. Integration allows to take this to the non-elementary level. When you have not a finite point, when you have not a just distribution of point masses, so if you 10 or 20 or even 1,000 point masses, but when you have a weight distributed continuously across some area. That's the only difference which integration brings into this picture. So with the integration, you can find, again, the pivot point, or center of mass. That's the official name for this from the physics language. It will allow you to find the center of mass points when the distribution of weight is continuous. So that's how you solve for it. Well, if you solve for it, it's a solution. That's a formula for the pivot point. All you have to do to see the analogy in a continuous one. So what happens here is this. You see, the bottom sum here is it's another typo, by the way. It's supposed to be equal sign here. I'm just putting typos one after the other. It's supposed to be equal sign here, of course. So it's a sum of all the weights. So it's a mass of the whole system. Yeah, it's a mass of the whole system. At the top, you have the sum of the individual masses multiplied by the coordinates where these masses are positioned. Yeah. And this column just gives you some sort of probabilistic look at the same formula. I don't know how much it's important, probably not much important, but still, you can give such a probabilistic interpretation to the center of mass formula. Yeah, you can give such a probabilistic interpretation. All we need to do now, we need to see the analogy of this formula for the center of mass when you look at the continuous distribution of weight, and that's what you do. When you have a continuous distribution of weight, you cross your line. First, you do the approximation, your step function, and you treat these individual boxes like point masses. The mass of each individual box is the height of the box times the underlying length times the density. So it's the area of the box times the density, approximate density of your material this thing is made of, and times the position where this box is, so xi. So this enumerator is the analogy of the enumerator from the slide before, but for n boxes rather than for 3 boxes or 3 point masses. At the bottom, you just have the total mass. So it's that's the length of the segment and well, actually, I said it wrong, as a matter of fact. We're finding, so I should say it actually, let me correct myself, I said it wrong. So rho here is not the height. So we're not looking at the flat region which we want to find the center of mass for. No, we're looking at the piece of a string or a rod whose weight or which density is proportional to rho at every point. So this is you have to imagine a rod sitting here. At every particular point, the weight of the little piece of a rod is this rho function at that piece times this length of the piece of a rod. It's right here, you see? The piece of the ith segment is the length of a segment times the average density at that place. And here you got the mass of that segment times the position of that segment. Both of the sums, they resemble a lot integration or integral sums. In fact, they are integral sums. If you take this to the limit, you will end up with 2 integrals like that. And this is a formula for the center of mass of a rod with a non-uniform density. If you have a piece of a metal string which has a non-uniform density, the density which given by the rho function, that's how you find the center of mass of that non-uniform rod. If your distribution is uniform, meaning that your rho function is constant, then this constant here will come up here. One integral cancels the other integral, and you will end up with the pivot point right in the middle of your rod. Yeah. And that's all there is to it. That's how you find the center of mass of a one-dimensional object with a non-uniform density. You can develop this to the 2 dimensions. In 2 dimensions, when you have some area on the plane, again of non-uniform density, but this time density is given by some function of 2 variables, and you interpret this density as this. You have the area. Every little piece of that area weights as much as the, you have some region of non-uniform density. Every little element of that region weights as much as the area of that region times the density at that point, quite expectedly. If you have such a conditions, mass of the whole area given by the double integral of this type, the pivot, the center of mass points, x bar, center of mass coordinates, x bar and y bar, these are the formulae for the center of mass coordinates. Yeah. So computationally, all you need to do, you need to compute 3 integrals for this region, and 3 integrals, and that will give you the center of mass point for that region. And that's a 3-dimensional case. If you have some solid in a space with a non-uniform density function of 3 variables, if you want to find the center of mass of that solid, this time you will need to compute 4 triple integrals. Yeah. There aren't many questions with the center of mass in the tutorial set. I published a tutorial set this morning, but there are a few. You will enjoy them, I hope. Actually, it's what happens normally when you compute these things. When you start with one of the triple integral or one of the double integrals, one of the approach which works for one, like a substitution, polar substitution or spherical substitution, it will work in the same way for the other 3, which means that computationally it won't be equivalent to computing 3 or 4 independent integrals. First one will be like a full computation, but the other 3 will be already shortened by your pre-computed values from the first computation. So even though to find a center of mass in 3-dimensional case, you need to find 4 integrals, in fact, the amount of work which is needed to be done will be less than 4 independent integrals. Yeah. Well, it's the last sentence here just explains what the centroid is. I'll be honest with you. Before I read this, I didn't know what the centroid is. So it is as new to me as it is new to you, or maybe to some of you it's not as new to it's not as new as to me. So apparently, centroid it's the lamina or solid body with constant density, and in that case, the center of mass will be called the centroid point of that object. Well, actually, it's quite expectable. Yeah. How do you call the point if you have a triangle and you have a point where all of the median lines intersect? How do you call that point? Center? Well, if you have a triangle, and it's a triangle which is made of made of a material of a uniform density, then the center of mass will be exactly at the point where all of the median lines intersect. And if you call it center, then it's quite expectable that for other bodies or other objects, they call it centroid. Yeah, so then it's quite expectable. Any questions? 2 examples here which compute center of mass. That's the first one. We'll just look into this. It's a triangle. It's almost the same example I just said, but this time the triangle is of non-uniform density. So if I need to find center of mass, I would need to compute 3 integrals, the mass of a triangle and then these x and y integrals. On the other hand, from the symmetry reasons, it's a good thing actually, from the symmetry reasons, you see my density function is symmetrical with respect to the vertical axis, it's just y. So the density on this side as good as the density on the opposite side at the same distance, meaning that my center of mass will be on the y-axis as well, meaning that I only need to compute 2 integrals. One is the mass and the other one where the y is actually. X I don't need to compute. In fact, it will be even clear from the integral itself. So let's just do that. So the mass is that's how you compute the mass. You take the triangle, multiply by the density. This is the repetition. It's a Fubini is applied. X integration from the left boundary to the right boundary, and y integration from 0 to 1. So at this stage, this triangle is treated as the x simple, right? X integration is the inner integration, which means that we treat the triangle as the x simple domain. And that's the evaluation. This y, I mean the integration with respect to the x, so y is irrelevant, we can pull it out. Oh, doesn't matter, that's the antiderivative, yx, it's a double substitution. 1 and 3, they say. How do they see that? It's y, take y, it's y squared. It's a negative y squared and negative another y squared, so negative 2 y squares. How is it 1, 3? 1 and 3. I don't know, maybe it is actually, I'm wrong, no. Anyway, I'll keep it like this. Maybe it is 1/3. Well, this the slide actually skips a few computational steps, but it's a one-dimensional computation. So first the integration, I think it's reasonable to skip this right now. I hope you can recover that one way or another. It's 1/3, that's the mass. When we go for the center of mass, that's what I said to you earlier, the symmetry of omega and the rho implies that x bar is 0, but for the y bar, that's what we need to compute, which is y squared, and that's the computations 1 on 6. So the center of mass, when you take the quotient of this integral and m, it's 1/2. So the center of mass actually exactly in the middle of this height of the triangle. It's exactly in the middle, that's right. Which contradicts to the fact, I mean, it would contradict to my earlier statement, because if the triangle, I mean, it would contradict if the triangle was uniformly distributed mass material. Because if it was, then the center of mass would be the intersection of median lines. We know that, I mean, I hope some of you know from the elementary geometry that when the median lines intersect, they intersect in the proportions 2 to 1, right? You remember that? So if the triangle was made of the uniform material, the center of mass will be still on this vertical line, but in the proportions 2 to 1. So it will be 1/3, in fact. Yes, it will be at the height 1/3 rather than 1/2. But the fact that the mass is distributed with the non-uniformly with the y factor, and actually y grows as you lift yourself off the 0 level, means that the more mass is distributed higher in the triangle. That's why the center of mass also gets lifted a little bit in comparison to the uniform location, in comparison to the centroid location. It's like it's an informal double check of this result. This result it probably is correct one. Is a correct one. Yeah. Any questions?
Geometrically, what does 1/3 and 1/6 correspond to?
Well, 1/3 it's a mass. It's physically, if you want to say. It's in just geometry. It's physically. 1/6. Well, there is a physical interpretation of that. It's called the momentum. Remember, let me guess. It's the same thing we did before. Look at this. If I go back to my this like a point-wise description here. Remember? Too much. This one. These quantities, when you multiply the mass by the length of the lever from the pivot point, we call them physics call it momentum. So when you multiply this mass by the x alone, without x bar next to it, it's again momentum, but taken with respect to the origin rather than unknown pivot. So this integral in the numerator, this 1/6, it's a momentum. It's a momentum of my triangle with respect to the origin, which is a quite like a essential quantity in physics. Yeah, so they do have the interpretation. 1/3 is a mass, 1/6 it's a momentum around the origin. Well, actually, I have to correct myself. It's not the entire momentum. When you have something wrong, someone disagrees. It's a momentum.
I think it's at the moment. I don't think it's momentum.
Yeah, well, okay, that's right, thank you. It's a moment, yes. My apologies. It's a moment, yes. Momentum is a different thing. Momentum is a different, yeah, that's right. Yeah, it's a moment, yes, thank you. This one, it's not the moment, it's the y component of a moment. I mean, when you have the one-dimensional case, all you take is the distance and the mass. But when you take the flat, like a two-dimensional case, you take a vector, because the moment is a vector quantity. You take a vector and multiply by the mass. So this one will be, because you only take the second component of the vector y, it will be the y component of the moment around the origin. Yeah, that's this. And the x component of the moment is 0 because of this moment.
So where is that center of mass anyway?
Where is the center of mass of this triangle with a non-uniform or uniform density?
For this question.
Well, it's in the middle, right here. 1/2. Well, 1/2 units above the 0 level.
Okay.
You disagree with that?
So we assume this triangle has uniform density will be a bit narrow.
If you assume the other question, when you have a uniform density, the center of mass will be 1/3 above the level. Yeah.
Okay.
Yeah. Any other question? Thank you. Well, it's the last one. It's a centroid. Again, sorry, it's a arc of a spiral, and this time we need to find the centroid, so the center point. So we assume that the density is uniform. For this question, we did half of the computation, or some of the computations. We computed the area, which is, if your density is 1, which is the same as the mass. So that's the number we found yesterday. These are the computations which you do to find the moment. So that's the x component of the moment, right? When you take x with uniform density, it's a polar substitution. I don't know how much you remember of yesterday's lecture at the moment, but we're basically reusing those things we did yesterday. But we just take that integral we had when we found the area of this area of the region under this arc, and that was the integral without this extra factor. And now we throw in this extra factor because that's a factor which corresponds to x under polar substitution. One way or another, again, well, this time the integral doesn't really look as a product of individual ones, but still you can do Fubini, right? That's a Fubini. Well, yeah, it's Fubini is down here. The blue R integral, it's R cubed by 3 with this substitution of the value like this. Oh, it says integration by parts 3 times. I'd say maple. Yeah, if I were you, I would do maple here. But you can do integration by parts 3 times and find this integral, yes. And this is the x part of the moment. X part of the moment of my region around the origin. Let's just see what happens for the y part. They don't say what, or they do. A similar computation, they say, will be the value like this. Yeah, for this region, of course, you can't employ any symmetry reasons. You need to do all of the integrations, even though, like I said, you can reuse the things we had from yesterday. Any questions?